Our next lemma is about the study of the structure of this L of A, the space of matrices that nil commutes with A. It is easy to see that the L of A is a vector space over FQ. And now it will be interesting to know what the dimension of L of A is over this finite field. And that is what we are going to do with our lemma 3. Lemma 3 states that for any A nilpotent over FQ, the dimension of the vector space L of A is equal to just n. And as a consequence of this, because this is a vector space over a finite field, we can compute the cardinality of L of A. For any A in the space of nilpotent matrices, the number of elements in L of A is precisely equal to q raised to the power n. Proof is not hard. Observe that if ny is equal to ya, then we will have, if you lift this n to the power k and multiply it on the right by y, you get on the right hand side y times a raised to the power k. By iterating the first equation k times. And if we let E sub I to be the row vector, where all the components are equal to 0, except for at the S component, we get 1, then E sub I plus 1 will be equal to E sub I times n. Because remember, n is a matrix where the first subdiagonal are equal to 1, where all the other entries are all equal to 0. And we will multiply vector E sub I on the right by n. It shifts the components of this vector to the right by 1, which gives you E sub I plus 1. And based on those two observations, given any matrix Y in L of A, we'll study the dependence relation between the rows of Y. And hopefully that will give us some information about the dimension of L of A. We want to prove that this dimension is equal to n instead of n squared, the dimension of the space of all n by n matrices. And we are going to find out for each matrix Y in L of A, the relations between its rows, which will provide us with some information on the restrictions of the matrices in L of A that will lead to this dimensional reduction from n squared to n. Now, for any y in alpha A, remember by definition this is the collection of matrices that nu commutes with A. And for any k greater or equal to 1, if we look at the k plus 1th row of y, the k plus 1th row of y can be written as e sub k plus 1 times y. That is why we want to study this property of e sub i's. So e sub k plus 1 times y will be equal to e sub 1 times n raised to the power k times y. This follows from this recursive relation we just derived. And this part will be equal to y times a raised to the power k by the new commutativity of y and a. This means for given matrix A, the k plus 1th row of y is determined by the first row of y. Here the k plus 1th row of y is this guy. And the first row is this part. And you should be able to see from here immediately that alpha A will be spanned by no more than n many elements. And to make this more precise, let us consider n matrices y sub 1 whose first row is E1 and second row is E1A, and the last row is E1 times a raised to the power n minus 1. Dot yn, where the first row is En and second row is Ena, all the way through the last row, which is En times a raised to the power n minus 1. And maybe let me erase all the arrows to avoid confusion. I have a habit of putting arrows above each vector, but here with the understanding that those e sub i's are all vectors, I feel like I don't have to put arrows above them. And we need to check the following. First, alpha A can be spanned by y1 through yn. This is because for any y in alpha A, if you write y to be y sub ij's, then if you just look at the first row, consisting of y sub i1 through y sub in, which can be expressed in terms of e1 through en, and you notice that all the other rows of y will satisfy this recursive relation, which is precisely described by the rows of y1 through yn. So y will be equal to y11 times y1 plus the y1n times y sub n. Once the first row is determined, all the other rows will be determined by the same relation. But this only proves this containment, that alpha A is contained in the span of those guys. We still need to prove that y1 through yn are in alpha A, so that the span is also contained in alpha A. To this end, we only need to check this new commutativity. So for y sub I in this set, we will multiply it on the left by n. This is n times e sub I a, all the way to e sub I a raised to the power n minus 1. And remember the structure of this standard nilpotent matrix N. So we can easily compute that this guy is actually just the first row. Now you get e sub I a all the way to e sub I times a raised to the power n minus 1. And in the last row, you're going to get 0. And this is same as e sub I times a all the way through e sub I raised to the power n. A raised to the power n will vanish because A is nilpotent. I'll explain this more carefully later. Let's see what this last term gives us. This last term gives us this matrix, this first row being e sub I, and the last term being e sub I times a raised to the power n minus 1 times a, by the block computation of matrices, which is just y sub I times a. And this tells you that y sub I is in L of A. And this is true for any I greater or equal to 1 less than or equal to n, which verifies this containment. But now, let me explain this equality in case you get confused. We only know that A is a nilpotent matrix, which means that A raised to some power will vanish. But how do we know that A raised to the power n will vanish? And I will explain this below. So the question is, why is A raised to the power n equal to 0? Where A is a nilpotent matrix. One way to see this is by looking at the Jordan decomposition of A in the algebraic closure of FQ. In this algebraic closure, A can be written as the Jordan form P inverse times J times P, where for each Jordan block of J, say J sub I is equal to the block where the diagonal terms are all lambda sub i's and the first subdiagonal are all ones. Since A is nilpotent, we know that A raised to power, say L, will vanish for some L greater or equal to 1. And this means lambda sub I raised to power L will be equal to 0 for any I greater or equal to 1 less than or equal to R, the number of Jordan blocks. But this lambda sub I must be in this algebraic closure. And in particular, this is a field, so it follows that lambda sub I is equal to 0 for any I greater or equal to 1 less than or equal to R. So, for this Jordan canonical form J, all the entries on the diagonal must vanish, and as a result, A raised to power n, which is equal to P inverse times J raised to power n times P, must be 0. Because if you look at each Jordan block, say this is a k by k Jordan block, and you lift this to the power n, it will vanish because n is greater or equal to k. And this proves that A raised to power n is equal to 0. Even if you start with any integer L, that makes A to the power L equal to 0. Now we have verified that alpha A is spanned by those n vectors. To prove that alpha A has dimension n over f sub q, it suffices to verify that those n vectors y1 through yn are linearly independent over f sub q. But that should be obvious to you because if you just look at the first rows of y1 through yn, they are already linearly independent. Those e1 through en are canonical vectors anyway, so the linear independence should be easy. But let me still write it down. So 1 and 2 tells you that the dimension of alpha A over f sub q is equal to n. That finishes the proof of the first part of lemma 3. And second part follows immediately from first part. The number of elements in alpha A is equal to q raised to power n, because by our definition, f sub q has cardinality equal to q, and any y in alpha A can be written uniquely as y equal to mu1 y1 plus dot of mu n yn with mu sub I in f sub q for any I from 1 through n. So there will be q times q times q times q raised to power n matrices. That gives you the cardinality of alpha A equal to q raised to power n. With this, we finishes the proof of this lemma 3.